Hello students, in this video we'll discuss beta distributions. A random variable x has beta distribution, has beta with parameters a and b distribution. Sometimes written beta of a, b. If its PDF has the form, if its PDF has the form FAB of x, FAB of x is going to be gamma of a plus b over gamma of a, gamma of b, and then x to the a minus 1, and then 1 minus x to the b minus 1, and here x is between 0 and 1. So this is a compactly supported distribution over here. Okay, excellent. So let me remind you, of course, we recall that the beta function of AB is exactly equal to gamma of A, gamma of B over gamma of A plus B. And so when I integrate this thing over here, so I'm really, in a genuine way, when I integrate this from 0 to 1, this is exactly equal to the beta function. So the beta function is also defined by the integral from 0 to 1 of x to the a minus 1, 1 minus x to the b minus 1 dx. So this coefficient out in front of this x, these powers of x's and 1 minus x's is exactly the right normalizing factor that you need in order for this to be a probability density function. Clearly this function over here is non-negative, so the non-negativity assumption is automatically satisfied. Great, so that's what these gamma random variables are. Now we're going to use a fundamental property of the gamma function. So the fundamental property, so if we recall from another video, so recall that the gamma function has this very special property. It has the property that gamma of x plus 1 is equal to x gamma of x, right? So it has this sort of this factorial sort of property. So what I'm going to do now is I'm going to use this factorial property. This is like a factorial property. Okay, to find moments of this gamma function. So let's do so. So let's do the first moment. So what's the expected value of x? So the expected value of x is going to be what? Is going to be gamma of a plus b over gamma of a, gamma of b, the integral from 0 to 1 of x times x to the a minus 1, 1 minus x to the b minus 1 dx. And we realize now that what this is gamma of a plus b over gamma of a, gamma of b. And what this thing is over here is now, this is the beta function at a plus 1, okay? So the beta function at a plus 1 is what? If I'm going to replace a, so this is going to be beta of a plus 1 b. And so if we simplify this, what we're going to get? We're going to get gamma of a plus b over a, gamma of a, gamma of b. And then I'm going to have a gamma of a plus 1, gamma of a plus 1, gamma of b over gamma of a plus b plus 1. So let's see what's going to cancel out over here. Of course, clearly this gamma of b is going to cancel. Gamma of b is obviously going to cancel. Now, what do I know about gamma of a plus 1 over gamma of a? Gamma of a plus 1 over gamma of a is just going to be equal to a. So gamma of a plus 1 over gamma of a is just going to be equal to a. So that's going to be an a. And then over here, gamma of a plus b plus 1, gamma of a plus b over gamma of a plus b plus 1 is 1 over a plus b. So it's going to be a 1 over a plus b. So this ratio over here is going to turn into a what? It's going to turn into just an a plus b. And so a over a plus b is the expected value of a gamma random variable. Let's find the variance. To find the variance, I need to find the second moment. So let's find the second moment. So the expected value of x quantity squared is going to help us find the second moment. And what will this be? This is going to be gamma of a plus b over gamma of a, gamma of b. And then let's figure out what I have over here. I put an x squared, so it corresponds to an a plus 2, right? So that's going to be a gamma of a plus 2, gamma of b, over gamma of a plus b plus 2. And so now let's carefully do this. Of course, clearly the gamma of b is going to cancel out again. And so, of course, gamma, I'm going to do two iterations of this factorial property. So I'm going to have gamma of a plus b, and then I'm going to have an a plus 1, and then I'm going to have an a, and then I'm going to have a gamma of a, all over gamma of A. And then I'm going to have an A plus B plus 1, and then an A plus B, gamma of A plus B, by using the factorial property twice. Now the gamma of A plus B will cancel, the gamma of A will cancel, and we just found the second moment. The second moment is exactly what? Is A squared plus A over A plus B times A plus B plus 1. Now to find the variance, I have to take this and subtract off the mean squared. So what's the variance going to be? So the variance of x, of this random variable x, is going to be what? Is going to be A squared plus A over A plus B plus 1, A plus B, minus the first moment squared. So that's going to be an A squared over A plus B quantity squared. Okay? And so now I can just add these fractions together. This is going to be an A squared plus A. I need another factor of A plus B, so I have an A plus B over there. And then this negative A squared over here is going to need a what? Need an A plus B plus 1 for a common denominator. And now my denominator is what? Is A plus B plus 1. And then an A plus B squared, Now let's see what cancels out over here. Let's look at all these terms over here. So what we're going to have, over here we're going to have an A cubed, an A squared B, an A squared, and then an AB. And over here we're going to have a negative A cubed, a negative A squared B, and a negative A squared. So let's see, so the A squareds are going to cancel, the A squared B is going to cancel, the A cubed is going to cancel, I'm just left with A times B. So in other words, what we have over here is we've just simplified this, so the variance now, the variance of this random variable is just going to be what? The only thing that's left is just going to be an A times B over A plus B plus 1 times A plus B quantity squared. And that is the mean and variance of a beta random variable. You can use this property over here, this factorial property, to find any moments of a beta random variable using this factorial property and then writing down the factorial many, many times. You can find the expected value of x to the power n for any n very easily using this factorial property. Thank you very much.